Hey friends, for today's episode, I'm going to need you to pop a bowl of popcorn. So head to your microwave, put in that microwave popcorn, pop it, but then stay at the microwave because we're going to stick around the microwave today talking about how we can use microwaves to create super thin ceramics that are awesome for spaceships. Hey everyone, welcome back to the Next Bite. On today's episode, we're talking all about ceramics. Before we get too deep into the weeds with MXenes, let's talk about ceramic thermistors. And as a part of this, we're going to be talking about today's sponsor, Mouser Electronics. They've got awesome technical resources that help engineers like Forbode and I stay up to date on what's going on. They're really well connected with industry, really well connected with academia, and they share their knowledge with everyone in these awesome technical resources, one of which we've got linked in the show notes for today, talking about PTC thermistors and how they're important in the automotive realm to make sure that circuits don't overheat. And they've got a compact design, which doesn't take up a lot of space, ideal for EVs, ideal for converters, battery management systems. Pretty interesting. And they're also made of ceramics, which relates really well to what we're talking about today.
I really enjoyed this one specifically because it's so easy to overlook all these little components that make up the products that we use on a daily basis. This one explicitly highlights why these ceramics are so important for applications like in the automotive realm. So again, if you want to learn a little bit more about the unsung heroes of the electronic world or get some more context about today's topic, I highly recommend this one. It was actually a pretty easy read too. I think like 2 minutes total.
Awesome. So we got that link to the show notes. Check it out. Now let's start talking about MXenes and ceramics in general.
Hold up. Real quick. I read it as MXene. Is it MXene?
I think it's MXene.
Okay, cool. I'm so happy you went first so I didn't give myself away like that.
It's MXenes. So I don't know. Folks, let us know if one of us is wrong, because we don't agree. So definitely one of us is. Maybe both of us are.
Just based on history, it's probably me. Because like 9 out of 10 times, it's me.
We'll see. MXenes. Super thin ceramics. They're highly lauded for their ability to block harmful radiation. They can protect electronics, protect spaceships, protect people. They're strong, light, electrically conductive. Great use in sensors and shields and flexible devices, but making them takes several hours, lots of heat, lots of energy, and also uses a lot of excess chemicals. And that's kind of a microcosm for how most advanced ceramic materials are manufactured today. So we're talking about a team from Carnegie Mellon that's developing a faster, more energy efficient method to create not just MXenes, but also ceramics in general. And there's a good video, we're going to link it in the show notes. Check it out.
The video's awesome.
Of the professor kind of explaining their entire thesis for their lab. And they kind of mention that like when you create ceramics, you have to heat them up typically. Like you get the constituent materials and then you have to heat them up a lot to get them to form into their final form. She kind of likened it to like boiling a pot of water. You can like take water and you can put it on the stove and heat it up inside a vessel from the outside, and it takes several minutes, like she said, tens of minutes for you to be able to boil a pot of water on the stove, which is relatable, right? And then she said the faster alternative to that would be like placing just a cup of water, exactly what you need, in the microwave, and you can boil it in a couple seconds. So she's like, there's kind of this paradigm here where you're using external heat inside a vessel to heat things up. It takes a lot of time, wastes a lot of energy, versus being very specific about where you need the energy to be directed and using a microwave to heat things from the inside out. So if you notice, the cup coming out of a microwave is not going to be as hot as the pot is as it's sitting on the furnace, because you're actually heating up the water inside the cup. You're not heating up the cup and then forcing that to transfer via conduction or convection to the water inside it.
I mean, tell that to my burning hand every time I try to grab my cup noodles when it's in the microwave. But that's besides the point.
You'd burn your hand way worse if you were trying to grab the pot on the stove.
That's a good point. And it's not new from us to recommend watching the media that's linked on some of these articles that come out. And I hate to say it, but the professor might have just done a better job than we're about to do of explaining what's going on here in 3 minutes.
Yeah,
so
for sure.
Again, highly recommend checking this out. Now,
Yeah.
like you just gave the perfect example in terms of, how fast and efficient you can boil a cup of water. And obviously we're relating it to ceramics here. And you hinted at it earlier. Like there's a lot of waste and pollution happening here. But the scale at which it's happening was a bit of a surprise to me. I think in the past when we've discussed pollution and emissions associated with like chemical processes, we've highlighted like concrete production a lot, like how it accounts for, I think, 8% of the global CO2 emissions. 1/3 of the global greenhouse gas emissions actually come from chemical manufacturing and production. So, yeah, I mean, we're talking about microwaving cups of water right now, but if this can be applied at scale to something like ceramics, the savings, not just in terms of energy, but the saving of our literal planet can be quite drastic.
And savings in terms of time too, right?
For sure.
It'd be interesting if you're like, all right, I'm going to reduce your energy consumption by 75%, but it's going to take as long, or it's going to take even longer. That's not as compelling as kind of the time trade-off they've got available here. But before we kind of jump straight to the finish line, I want to talk a little bit more about MXenes themselves. So they're 2D materials. They're not actually two-dimensional, but they're very, very, very thin, infinitesimally thin. So we call them two-dimensional materials, meaning that like in X and Y, so in length and width, they can be very broad, but in terms of thickness, they're very, very thin. And the way that they're usually derived is by removing layers from max phases. And max phases are these blocks of metal and carbon and nitrogen together. So if you get a really, really thin layer of a max phase, you get a MXene. And that's where I'm getting my pronunciation of max, or my guess on pronunciation of max. But basically these really, really strong, light, electrically conductive, radiation blocking shields that are flexible. They could be really useful in spacecraft, electronics, military gear, batteries, sensors, shields, all these types of different devices. But the reason why that's so important, I'm actually reading a tweet here from my friend Huberthy Blow. He tweeted yesterday or the day before, "Today I learned that GPUs only last 2 to 8 weeks in space. Radiation destroys them. You've got to launch a new satellite to replace them. This is a huge problem for AI in space." Right? So a lot of people are talking about like putting satellites into space. They can do tons of computing. It's really cool. But without a radiation shield like a MXene, your GPUs might be fried in 2 to 8 weeks because of radiation. So that's what makes MXenes so important. But making them the old way typically takes about 40 hours per batch, requires a ton of energy, requires a ton of heat, and also creates a bunch of chemical byproducts. Like making chemicals this way is very inefficient, and it's not going to let MXenes create the amount of impact that we want, which is like, hey, shield all our GPUs so that we can put satellites in space and they last forever.
Yeah. And, when it comes to microwaving, I'm going to go back to cooking for a second. Some might say that when you blast your broccolis with microwaves, they might not taste as good, or the texture might not be like what it could be if you handle it on the stovetop yourself, right? So the question that came to my mind is, it's great that we're getting all these savings in terms of energy consumption and time, all the good stuff, but is the end product still the same when you're drastically changing the heating process here? And I was surprised to learn that apparently structurally there are differences, but at least when looking at MXenes for radiation protection, the performance is pretty much on par to what they were getting using conventional approaches.
Yeah, exactly. So, maybe your broccoli doesn't taste quite as good when it's been microwaved, but your MXenes will taste just the same. Also,
yeah,
interestingly,
MXenes.
when I was in my only elective in college was a cooking class, and I just so happened that like the textbook that we used for that course was The Food Lab by Kenji Lopez Alt, who's my favorite food writer of all time. He's a scientist turned chef, so he's like, I think he thinks in a very similar way that I do as an engineer. Most vegetables he mentioned aren't preferable to cook in the microwave, but asparagus, for some reason, I've got to go back to the Food Lab and read it and understand why. Asparagus, he said, was the best way to cook asparagus is in the microwave.
Well, I'm not going to speak on texture, but I was reading another book called How Not to Die, which is a pretty aggressive title, but it's all about eating well. And it said the way to retain the most nutrients for a vegetable is to cook it in the microwave and actually not on the stovetop. So in terms of quality, I guess the microwave seems to be your best friend across all industry and applications.
And not just for food, also for making MXenes, right?
That's what I'm saying.
Just to talk a little bit more about the mechanism here. So we alluded to it in the beginning. Indirect heat, or even direct heat from a furnace, right? You get a furnace really, really hot, and then you've got a vessel that's holding these MXene ingredients inside of it, and you use the heat to trigger the reaction to heat the ingredients. But it's like heating water inside a pot on the stove. And it's actually even more like heating water inside a pot inside your oven and waiting for it to boil. That's what's going on here. And it either uses a furnace or a very, very hot acid bath. And it takes up to 40 hours for these MXene ingredients to complete the reaction. Mm-hmm. Requires a lot of energy. They basically liken this to the opposite, which is like putting it in the microwave, like microwave popcorn, where it heats up the popcorn from the inside of the kernel, and then the reaction happens, and then pop, it happens all at once, and then it's done. That's kind of what happens in the microwave method here. So it uses microwave energy that's specifically tuned to the ingredients in the MXenes to get them to react quickly, as opposed to taking 40 hours in a furnace or 40 hours in an acid bath. They're able to complete the reaction in 90 minutes, and the energy use is 75% less than the furnace. So it's like it's like a 30-to-1 ratio in terms of time, and it's a 3-to-1 ratio in terms of energy.
It's incredible. And my number one question was, if the performance is so good, right, why is this not being deployed at scale right now? And they had some good feedback in terms of next steps. So they've already done some quick analysis in terms of performance for MXene specifically. Like I said, they've noticed structural differences, but in terms of radiation protection, it seems to be pretty on par. The next step for them is to actually do a larger scale MXene shield and do some thorough testing for radiation protection. I think if that goes well, we're going to start seeing industry partners being involved with this project to see if they can scale it up, not just for aerospace applications, but obviously, like we were talking about at the beginning, there's quite a lot of ceramic production happening for electronics and so on and so forth.
Yeah, and that's kind of what this lab is focused on, is not just MXenes, right? Ceramics as a whole. MXenes are just an awesome application of ceramics, literally a space age application of ceramics. They might be able to take the same technology and go apply it to other types of ceramics. And the professor even mentioned maybe even beyond ceramics, right? Other types of material synthesis. Let's figure out a way to use less energy, to use it less time. And like you're mentioning for both, there's a lot of room for us to improve our chemical production and our material production in terms of emissions. Would you say almost a third of the world's total emissions?
Yep, 1/3. And again, not only, you said it best, not only is it good for the planet, so you can feel good about it, but if you are a profit-hungry capitalist, the win of time efficiency and a lower power bill is going to be pretty convincing for you to hopefully act as a catalyst in terms of adoption of this technology, right?
Yeah.
So win-win across the board.
We love win-wins.
We really do. Really do. You wanna wrap this up?
Yeah, I'll wrap it up quickly here. All right, folks, what do radiation shields for space and popcorn have in common? Turns out that your microwave can make both, but one of those is going to end up in space. So the old method of creating MXenes, these ultra-thin ceramics that block radiation, takes 40-plus hours, lots of heat, lots of emissions. This new method from Carnegie Mellon, microwaves can cook it in under 90 minutes using 75% less energy. Still works just as well for blocking X-band and other types of radiation. They've got a tunable recipe where they can change the time or power and ingredients to change the final performance, and they think this is going to be a big win for defense, space, and electronics.
Money. That's the pod.